We've discussed a various number of types of strategies for integrating functions. And one of the final types that you'll need to know in this course is what's called integration by parts. And it's a technique that's meant to deal with integrating products that really don't contain any valid use substitution. And where typically one of the functions or factors of the integrand are what's called a transcendental function. That is, a transcendental function is a non-algebraic function, so non-algebraic, if you will, that kind of transcends finite combinations of algebraic operations. And I know that definition might seem a little dense. So if we really just kind of think about functions like e to the x, natural log of x, logarithmic functions, trigonometric functions, right? Trig functions. These are all examples of non-algebraic transcendent functions or transcendental functions that that aren't really just a set of finite combinations of algebraic operations. So I want to at least highlight an example of this. So for example, something like x times e to the x dx. This would be an example of a function that would be a really good candidate for integration by parts. Well, why is that? Well, one, if you look at that carefully, really, there's no valid u substitution approach. If we set u equal to e to the x, there's really no way for us to just write that as du in there. At the same time, it doesn't seem like it's going to result in any inverse trigonometric function or result in a natural log function. So up to this point, there's really no way for us to actually deal with these types of functions other than to use what's called integration by parts. So now that we know that u sub doesn't work here, and we recognize that one of our factors here in our integrand, e to the x here, is a transcendental function, this would make this a really good candidate for integration by parts. Well, how does integration by parts work? Well, first off, let's talk about kind of the derivation of the rule for integration by parts. What are we saying here? We're saying that the derivative of the product of two functions, u and v, so the derivative of u times v is equal to v times the derivative of u plus u times the derivative of v. This is really just the product rule in action. That's all we're doing. This is just the product rule. In other words, this is v times u prime plus u times v prime. Now, if I were to integrate the derivative of u times v with respect to x, right? So if I'm just integrating this side, if you will, if I integrate this side, that's equivalent to integrating the result of the product rule here. So the integral of v du dx plus the integral of u times dv dx. Now, all I'm doing from here is I would then say, okay, well, the integral of the derivative of u times v, according to the fundamental theorem of calculus, is just u times v. And what I have left over here is the integral of v with respect to u plus the integral of u with respect to v. You can think of this kind of notation-wise as kind of just dividing these out here, okay? So if that's the case, the integration by parts formula is just a rearrangement of this final integral. That is to say, if I wanted to isolate the integral of u times dv, I would subtract the integral of v du from both sides. And what we're left with is a nice little formula here that says the integral of u times dv, or the derivative of v, if you will, is equal to u times v minus the integral of v times du. And it's a really simple derivation there. And an easy way to remember this formula, something that I'll often tell my students, is the phrase ultraviolet, this should be one word, ultraviolet voodoo, if that helps at all. Right? So we say ultraviolet voodoo to kind of help you remember that structure there. So to find the integral of u times dv, it's equal to uv minus the integral of v du. Now let's go back to the problem that we were looking at and let's actually try to apply that. So the first thing that we need to do, once we've established that we do need to use integration by parts here, is to define all of our variables here. Let's let u be equal to what? And dv be equal to what? Now, to help guide us into as to this deciding on which variable or which of these parts each variable is going to represent, as some quick guidance here. I typically recommend to let dv be the more complicated part of the integrand that can be easily integrated, and that's often the more important rule. dv should be something that you can easily integrate. If you're having a hard time integrating, or we see that the integral is really complicated, chances are that that was not a good function to choose for dv. U also, we want to be the part of the integrand whose derivative is simpler than itself. So if we're differentiating u to get du, and we see that we get something really complicated, that probably also wasn't a good candidate for u. So looking back at this problem with that in mind, ask yourself what would make the most sense to choose for our u, and which would make the most sense to be our dv. And hopefully we're seeing that u should actually be equal to x. We'll call this one u. And dv then would be e to the x with respect to x. E to the x dx. This would be our dv. Well, why is that? Du, that derivative is very simple. The derivative of x is just 1, so we can just say du dx. The derivative of x is just 1 times dx, or 1 dx. dv, this is a really easy function to integrate as well. This is equal to e to the x. Now, there will be some cases where we can actually switch this around. It doesn't really matter what our u is, what our v is. And there will be some cases where it really absolutely matters, because otherwise we can't proceed with the question or with the problem. So now that we've defined our variables, we can just apply the formula. We can just say the integral of u dv is equal to uv, and I should probably erase these, uv minus integral v du. So u times v, x times e to the x, minus the integral of v du, which is dx. Oh, well, the integral of e to the x is pretty simple. This is just x times e to the x minus e to the x plus our constant c. Okay? All right. So something that might be helpful for us is to actually go through a couple of functions here and determine whether or not we need to use integration by parts. So for these problems here, I want you to pause the video right now and see if you can determine which of these functions require u substitution, or which of these problems actually need to be done by using integration by parts. And there are actually a few here that could be either neither integration by parts or u substitution, or either method. So pause the video and see if you can think of these. And as you're going through, if you determine that we need to use integration by parts for that problem, just go ahead and define the variables there. Don't worry about actually doing the integrating. We'll do that in a moment. And if u sub is possible, then go ahead and finish integrating using u substitution, since that is a method that we're pretty familiar with at this point. Okay, so if you've had a chance to go through this, the first one we would say, let's just kind of go through a few of these. This first one, I determined that integration by parts is the way to go, where u would be x squared, dv is equal to sine 2x, du is equal to 2x dx, and v is equal to negative 1/2 cosine 2x. Okay. The integral of x times sine x squared, and then if we can just group that, hopefully you saw that u substitution is actually pretty valid there, where I would set u equal to x squared, in which case du is equal to 2x dx. And for the sake of time, I'm not going to actually show all the work for all of this, but you should end up with negative 1/2 cosine x squared plus c as your integral. Okay. All right, let's look at number 3. This was something where integration by parts is required, in which case u is x squared, du is equal to 2x dx, dv is e to the 5x, and v is equal to 1/5 e to the 5x. Number 4, u sub actually works here. So we'll set u equal to 2x to the 7, du is equal to 14x to the 6th dx, and dv then is no longer required. And again, if you would like to integrate that on your own and check your work, you have 1 over 14 to the 2x to the 7th power plus c as our integral. Number 5 was one where both methods actually work. And if you did integration by parts, u would be natural log of x, du would actually be 1 over x dx, dv is 1 over 2x, and v is equal to 1 over 2 natural log of absolute value of x. And if you wanted to use the u sub method, that looks more like a v, the u sub method here, the way I set this up here is to set this as 1 over 2x natural log of x dx, and then rewrite this as 1/2 the integral of 1 over, or let's just actually do this, natural log of x 1 over x dx, and hopefully we see that this is our u, and this is our derivative of u, so our integral should just be 1 over 4 natural log squared x plus c. Okay, so either one would actually work for number 5. For number 6, parts is the way to go. So this is natural log of x, du then is 1 over x dx, and then dv would be x, and v would be x squared over 2. Number 7, if you thought about this one enough, hopefully you saw that neither integration by parts or u sub actually work here. This is actually a function depending on whether or not you divide the numerator by the denominator or just add and subtract a 1 in the numerator. Hopefully we actually see that this is something that results in an arctangent. Okay. And finally, for number 8, this was an integration by parts. U sub does not work here, in which case we can redefine all of our variables as such. We've done this a couple times now. Okay. All right. So now that we're hopefully pretty comfortable determining whether or not integration by parts is necessary for the problem, let's actually practice some integrating using this method of integration by parts. Okay. Let me start with number 9. So looking at this particular problem here, we're going to say, all right, think about what would make the most sense for our u and what would make the most sense for our dv. Well, I want dv to be something that I can easily integrate and u to be something whose derivative is simpler than itself. So I'll set u is equal to x and du is equal to dx. That means dv is going to be sine of 3x dx, in which case its integral is negative 1/3 cosine of 3x. So applying the ultraviolet voodoo formula or integration by parts formula, we can say this is ultraviolet minus integral of v du. v du. Okay, and we can clean this up a little bit. We can say this is negative x over 3 cosine 3x. If we move that one negative to the outside but integrate here, we see that we need a 3 in here, so we would say that this is plus 1/3 times 1/3 sine of 3x plus c. Okay? All right, let's try something like number 10. Pause and think about this one. Which would make the most sense to have be our u? Well, in this case, hopefully you saw that it didn't really make sense to have arc sine of x be our dv here, because then we would have to integrate it. And the whole point here is that we don't actually know how to integrate this. That's why we're doing this problem. So we really don't have a choice other than to let u be equal to the arc sine of x. And fortunately for us, we actually know what that derivative is from our lessons in the previous chapter. So we can say the arc sine of x, du is 1 over root 1 minus x squared. dv is equal to dx, and v is equal to x. So applying the ultraviolet voodoo, we can say ultraviolet, which is x, and I'm just going to put that x in front, minus the integral of v du and this we can clean up a little bit here. We can rewrite this as the integral of x. Well, let's do this. Actually, let's take this 1 minus x squared, and let's set this to the negative 1/2 power. We're just rewriting this in rational exponent form. And if I set this, kind of think about this as my u, my du would be negative 2x. So I would need a negative 2x dx. So to have that negative 2 in there, I need to also multiply by negative 1/2, which I'll just move to the outside. And once I clean all that up, I've got x arc sine of x plus 1/2. The integral of this, now that I can do the u sub or unhook the chain, if you will, I'm going to just get 1 minus x squared, write this to the 1/2, all of this over 1/2 plus c. These divide out, and we're left with x arc sine of x plus root 1 minus x squared, all of that plus c. Okay? All right. Let's do a definite integral problem. Let's try something like this. Well, u in this case probably make the most sense to have be our natural log of x, because I know how to differentiate that easily. That's 1 over x dx. dv would then be equal to x squared dx, and that's pretty easy to integrate. That's just x cubed over 3. So ultraviolet voodoo, we'll say natural log of x times x cubed over 3 minus the integral of v du. And we're going to evaluate all of this here at the bounds e and 1. Okay? So let's finish integrating this first. So we've got x cubed over 3. I'm just going to rearrange the terms. Minus, and I'm going to move that 1/3, this 1/3 to the outside. So minus 1/3, the integral of x squared dx. Again, we're just evaluating this from 1 to e, which then is pretty easy to integrate. This is just going to be minus x. So the integral of x squared is x cubed over 3. X cubed over 3 times negative 1/3. But since I have a 3 down there, I'm just going to rewrite that as negative x cubed over 9. That's 1e. And hopefully you know how to kind of plug in from there, but you should end up with e cubed over 3 minus e cubed over 9 plus 1 over 9. All right. Okay. So let's go ahead and do one more type of problem here. Let's go ahead and try this next one. Pause the video and see if you can integrate this one using integration by parts. Well, this one, u would probably make the most sense to have the natural log of x squared plus 1. Du would then be 2x over x squared, x squared plus 1 dx. dv would then be dx, and v would be equal to x. So, ultraviolet voodoo, natural log of x squared plus 1 times x, so I'm just going to put that x out here so we don't confuse it as being part of the argument, minus the integral of v du. Okay, and bring this down. So I'm going to move that 2 to the outside, so I have just x squared over x squared plus 1 dx. And similar to what we did in the previous problem, if I add 1 and subtract 1 here, this then allows me to say the following, and I should be putting equal signs. Minus 2 times the integral of 1 minus 1 over x squared plus 1, all of that dx. So, and we integrated this previously, this should just come out 2 minus 2. The integral of 1 is just x. The integral of 1 over x squared plus 1 is arc tangent of x, and all of this plus c. All right? So hopefully you're pretty comfortable now using integration by parts, and in the next lesson we'll talk about advanced integration by parts and the tabular method.